Buffer has a pH unaltered on keeping for a long time. If you keep buffer solution for a long time also, its pH will not alter. When acid is treated, H plus ions will be liberated and some of the unreacted ions will be present. With that unreacted ions, this NaOH, which is a base, will be reacting. After addition of small quantity of acid or base, the capacity of buffer will not change. Hello everyone, this is Harshita Bhavasar from Vidhyaashram PU College Temple of Excellence. Today I am going to start session 7 from the chapter Chemical Equilibrium. In the last session we have discussed about Lewis concept and limitations of Lewis concept, also ionic product of water and dissociation constant also we have discussed. In today's session we will discuss about buffer solutions, pH of buffers, that is Henderson's equation, and buffer capacity with some of the illustrations or numericals. Now we will see buffer solutions. Buffer solution may be defined as solution of constant pH. Constant pH means constant acidity or constant basicity should be there, and which resists the change in pH when a small quantity of strong acid or base is added to it. Usually what is buffer solution? It is a solution. What is its property? It has to resist the change in pH and also it should maintain the constant pH. Okay. Even after a small quantity of strong acid or strong base is added to that any other solution. And what is the characteristics of buffer solution? Buffer has a pH unaltered on keeping for a long time. If you keep buffer solution for a long time also, its pH will not alter. pH is altered by dilution. How it can be altered? By dilution. Dilution means by adding water, the concentration of any acid or base will be changes. You know that. So, by that pH will be altered by dilution. pH is altered by the action of small quantity of strong acid or base to it. The pH buffer will be changes. When it will be changed, the strong acid or base in a large quantity will be added. This is about buffer solution and the properties or characteristics of buffer solution. Next, types of buffer solution. Okay, there are 3 to 4 kinds of buffer solutions are present. In that, various types of buffers are known. They are normally classified as follows. Usually acidic buffer, basic buffer, salt buffer and ampholyte buffers are present. First we will see what is acidic buffer. Acidic buffers which contains a mixture of weak acid and its salt with a strong base. Okay, weak acid and its salt with a strong base usually will prepare a acidic buffer. Examples: acetic acid plus sodium acetate, boric acid plus borax, citric acid plus sodium citrate. These are the 3 examples of acidic buffers. Next, basic buffers which contain a mixture of weak base and a salt of it with a strong acid. Weak base and its salt with a strong acid. Example: ammonium hydroxide plus ammonium chloride, glycine plus glycine hydrochloride. These are the 2 examples of basic buffer. The third type of buffers is salt buffers which contain a mixture of an acid salt and a normal salt of a polybasic acid. See here, Na2HPO4 and Na3PO4, sodium phosphorate acid, and this is sodium bicarbonate and sodium carbonate. The fourth type, ampholyte buffer, which contains a solution of single compound having both an acidic group and basic group. Means it is having the mixing of both of an acidic group also basic group. Example: amino acids. Overall, there are 4 types of buffer solutions are there. Those are acidic buffers, basic buffers, also salt buffers and ampholyte buffers. The explanation of buffer action, how the buffer action will be carrying out, we'll see. The resistance to pH, change in pH by a buffer on the addition of small quantities of a strong acid or base is called buffer action. Buffer action of acid or basic buffers are explained as follows. Means we know that buffer solution will be used to resist the pH change. Okay, after addition of small quantity of strong acid or strong base, the acidity or basicity will not change in the solution. Now we will see how it will be action, will do its working. Acidic buffer, consider a mixture of acetic acid and sodium acetate. Here a mixture of acetic acid and sodium acetate will take. Acetic acid is a weak acid, we know that, and ionizes partially, while sodium acetate undergoes complete ionization. Here the mixture of weak acid and strong acid we have taken, which weak acid will undergoes partially ionization, sodium acetate will undergoes complete ionization. This is acetic acid, will go partially CH3COO minus plus H plus. This is sodium acetate, CH3COO minus plus Na plus, and here in the water H2O will give H plus and OH minus. On dropping and adding a drop of HCl, more H plus ions are introduced. These H plus ions combine with the acetate ions to form feebly ionized, that is CH3COOH. pH remains a constant. Here what they are adding to check? A drop of HCl, it will liberate more H plus ions with the acetate ions to form feebly ionized in acetic acid. And here the pH remains constant. Here we are explaining about acidic buffers. When a drop of NaOH, which is a base sodium hydroxide, is added, OH minus ions of the base react with unionized acetate ion and water. When acid is treated, H plus ions will be liberated and some of the unreacted ions will be present. With that unreacted ions, this NaOH, which is a base, will be reacting. That time it will react with water and unionized ions. So that time also no change in pH. So what is the overall reaction? Acetic acid plus OH minus will form CH3COO minus plus water molecule. This is the buffer action, that is mainly acidic buffer action. We'll see now basic buffer. Consider a mixture of ammonium hydroxide and ammonium chloride. The following ionic equilibria exist in the solution. This is ammonium hydroxide, ammonium ion plus OH minus. This is ammonium chloride, ammonium ion plus chloride anion will form. This is normal water ionic equilibrium. When a drop of HCl is added, the H plus ions introduced combine with ammonium hydroxide and form NH4 plus and water molecule. Here also HCl will be added to check for the ammonium hydroxide. What will happen? Ammonium hydroxide will react with H plus ion, which was liberated from HCl, and it will form NH4 plus H2O molecule. Next, they will treat with a drop of NaOH, which is a base, added. The OH ions introduced react with ammonium ions and form feebly ionized NH4OH. pH remains constant. First we will add acid to liberate H plus ions. Next they will add a drop of NaOH, which is a base. That time whatever the ionization will take place in the above reaction, that is NH4 plus, with that OH minus, which is liberated from base, will be reacting. So what will happen? NH4OH will be formed. But here what you have to observe, pH remains constant. In both the acidic buffer and the basic buffer, what is the purpose we are using? The purpose we are using to resist the pH change. That purpose was fulfilled by this, seeing the explanation of buffer action. Next, pH of buffers. What is the pH of buffers will be there before it can resist some of the solution. Acidic buffer. Consider an acid buffer containing a weak acid and its sodium salt. Okay, weak acid with its sodium salt. This is weak acid Ha and it will liberate H plus and A minus. This is sodium salt Na plus A minus. Okay. This is dissociation constant. The molar concentration of H plus ions into molar concentration of A minus ions divided by molar concentration of weak acid. Okay. If you want to see molar concentration of H plus ions, we have to take left hand side equal to dissociation constant of concentration of weak acid by A minus ion. In an acid buffer, due to common ion effect, the ionization of the weak acid is largely suppressed. Okay, in an acid buffer, due to the common ion effect, the ionization of the weak acid is largely suppressed. Hence, concentration of Ha, that is weak acid, may be taken as the molar concentration of acid taken. Here, due to the common ion effect, the ionization of weak acid will be suppressed. That's why they are taking in the concept of molar concentration of acid taken. Next, sodium salt is completely ionized and it can be assumed that all the anions, that is A minus, come from sodium salt. Hence, concentration of A minus ion equal to salt concentration. Okay, whatever here concentration of A minus will form, that will be considered as salt concentration. So here concentration of H plus equal to dissociation constant of Ka, that is Ka, concentration of acid divided by concentration of salt. If we relate with log, minus log into concentration of H plus equal to minus log Ka minus log concentration of acid by concentration of salt, then it will form minus log into H plus, means it will be considered as pH equal to pKa minus log of acid by salt, concentration of acid by salt. What will happen? pKa plus log, that salt by acid will form. Next is basic buffer. This is the main derivation to bring pKa plus log of concentration of salt by concentration of acid. Same thing you have to analyze with basic buffer. On the same basis for a basic buffer, POH equal to pKb, this is base, plus log into concentration of salt by concentration of acid, and pH will be equal to 14 minus POH. This relation, if you know, you can understand this derivation. This is about the pH of acidic buffer and basic buffer with its derivation. This is a small 3 to 4 step derivation, but if you understand this concept, you can do the numericals very thoroughly. Next, application of buffers. Where we are using these buffers? Many industrial processes like manufacture of paper, dye, ink, paints, drugs, dairy products use buffers. In the preservation of various foodstuff, main application only to resist the pH change. Foodstuff we have seen in our daily life, many products are coming to the market like many instant foods, and we can store in our refrigerators. Whatever it is, if you want to resist the pH, you want to add that buffer. pH of blood is maintained at 7.4, slightly alkaline, but by two buffers, carbonic acid and sodium bicarbonate. An acid salt buffer of phosphoric acid containing H2PO4 plus and HPO4 minus, enzyme catalyst metabolic reactions takes place at the pH of 7.4. Here the mechanism of pH of blood they have explained by carbonic acid and bicarbonate and also phosphoric acid. This is about the applications of buffer. Next, buffer capacity. Buffers keep the pH constant even after the addition of small quantities of a strong acid or base. What they are telling? Buffers keep the pH constant even after the addition of small quantities of a strong acid or base. How much it is capacity is having means, after addition of small quantity of acid or base, the capacity of buffer will not change. If larger quantity of a strong acid or strong base is added, a change in pH may take place. If we have changed the quantity of strong acid or strong base, then it may change. Buffer capacity is defined as the number of moles of acid or base to be added to 1 liter of buffer to effect a change of pH by unity. Buffer capacity equal to number of moles of acid or base added to 1 liter of buffer divided by change in pH. Okay. For an acidic buffer, when concentration of salt equal to concentration of acid, pH equal to pKa. And for a base buffer, when concentration of salt equal to concentration of base, pOH equal to pKb. These relations are very much important. Buffer capacity is maximum under these conditions. pH of such buffer does not change at all, even addition of large quantities of acid or base. At this stage, if this stage salt concentration or base or salt concentration with acid, if it is in this relation, if we add large amount of strong acid or base, it may not change. That is, greater buffer capacity of buffer solution implies greater power to resistance in the change. That we know by seeing the capacity relation only. If the capacity of buffer is greater, the resistance of pH will be greater. Next we will see some of the numericals. The degree of dissociation of 0.2 molar acetic acid, that is Ka will be 4 into 10 to the power of minus 5 is, what will be the degree of dissociation? Okay, we know that C alpha square equal to Ka, or alpha will be equal into root of Ka by C. This is the formula you should know for acid, that is dissociation constant of acid. Here we have to understand we have to calculate what is alpha. We have taken alpha, square we have to implement means root you have to put Ka by C. Alpha equal to Ka is 4 into 10 to the power of minus 5 divided by 0.2. Okay. This one you have converted 2 into 10 to the power of minus 1. Then 2 into 10 to the power of minus 1 equal to 1.41 into 10 to the power of minus 2. Okay. This is the answer, means 1.41. A will be the answer. Okay. Next, the buffer action of the blood is due to the presence of carbonic acid and bicarbonate. If the ratio of the above buffer is 1:20, the pH of the buffer is pKa equal to 6.097. What will be the answer? We know that relation pH equal to pKa. We are using the buffer action of blood. Okay. pKa plus log of concentration of salt by concentration of acid. If you want to do pH, pKa we know 6.097 plus log 20. Here they have given. So log 20 will be 1.3010. Your answer will be 7.3980. Okay. Here answer will be B. Next, a buffer solution of pH 8.95 was prepared from ammonium hydroxide and ammonium chloride. The mole propagation of ammonium chloride and ammonium hydroxide is pKb will be 4.7447. This is also same relation, pOH equal to pKb plus log of concentration of salt by concentration of acid. Okay. pOH equal to 14 minus 8.95 equal to 5.05. We have discussed that pOH equal to 14 minus pH. For that relation we have seen first 5.05. For pOH we got 5.05 equal to pKb plus log of salt by acid. pKb we know 4.7447 plus log salt by acid. See here, log of salt by acid will be equal to 5.05 minus 4.7447 equal to 0.3053. Antilog if we take, it will form 2.019. It will be 2:1. Okay, the salt and the base are in the proportion of 2:1. And which of the following is not a buffer? In the following mixture, which is not a buffer? Ammonium hydroxide and acetic acid is not a mixture of buffer. I hope you have understood completely about the buffer action, buffer capacity and types of buffers. In the next session, we'll see salt hydrolysis, solubility product and common ion effect on solubility of ionic salts. This chapter is very much important, so you have to analyze with numericals. I hope you have completely understand whatever I have taught today. We'll meet in the next session. Thank you.